Now, how do we use historical climate data to support climate risk assessment? The usage of historical climate data to support climate risk assessment depends heavily on the impact assessment approach we adopt. Typically, assessment approaches are classified into top-down and bottom-up approaches. Top-down approaches emphasize understanding the plausible impacts by representing different sources of uncertainty. And typically, this approach results in what we call a cascade of uncertainty. For example, it starts with a representation of different climate scenarios, global climate model simulations, a possible downscaling step, and assessing the range in outputs from a particular climate model. For this kind of approach, long-term data greater than 30 years, either station, gridded, or reanalysis datasets are required. The other approach is a bottom-up approach, which starts with an attempt to identify the nature of climate risks, such as floods, droughts, and heat waves that a system is exposed to under past and current climate. Under these circumstances, for the bottom-up approach, real-time station data, satellite data, and radar estimates are very important for stress testing the system or doing a sensitivity analysis of water infrastructure to climate change. So, station data versus gridded data. The usage of station versus gridded data depends on the scale of analysis. For example, for a spatial climate risk assessment involving accounting for joint adaptive capacity across locations, we will typically require gridded data sets such as reanalysis, satellite, and radar estimates, while for a site or point climate risk assessment, we will typically require station data for those kind of assessments. The temporal resolution is also very important, and this will depend on the level, that is the detail of the climate risk assessment. For a very high level climate risk assessment, seasonal and annual summaries of hydrometeorological variables may suffice. Whereas for detailed climate risk assessments, down to sub-daily and daily sequences of meteorological and hydrological variables may be required. It is important to understand how to extract data at engaged locations. Use of station data that is climatologically similar to your project site is recommended. Test for climatological similarity and use data from a nearby station if your project site does not have a weather station. You can also apply regionalization techniques to determine station similarity. In the absence of station data, make use of gridded data. And to make use of gridded data for your project site, extract data from the project location using one grid or 4 surrounding grids. Variables such as precipitation will typically require averaging over multiple grids to reduce the impact of smoothing, which occurs during interpolation of station data to produce gridded data sets. Example uses of climate data for risk assessment. For a very detailed climate risk assessment, for example, design of new climate resilient infrastructure, will typically require 30 years of precipitation data analyzed for specific sites and locations. For moderate assessments, such as risk assessment of all dams in a given region, will typically require threshold data, for example, number of days exceeding 35 degrees Celsius. Characterizing historical climate data and impacts is important. Typically, we will ask what impacts have already occurred. Start by obtaining observed historical climate data at a local climate station and analyzing average conditions and trends. Then compile anecdotal evidence based on local observations. We also used observed historical data, observed data to develop application-ready climate projections. So historical climate projections are biased when compared against observations, and we typically apply a post-processing step known as bias correction to produce application-ready data. So on the top panel here, you can see the observations, the black line, is far below what the climate model gives us during the historical period. So we typically apply a bias correction technique to move the climate model output closer to the observations. So this is where observations connect with climate model simulations when doing climate risk assessments and developing application ready data to support those